common base for. And then we're going to solve logarithmic equations using laws of logs, and then identifying extraneous roots for logarithmic equations. So for example, solve the following exponential equations algebraically by taking the log of both sides of the equation, then using laws of logs to isolate and solve for x. So if we're given the following exponential equation and we are asked to solve this algebraically, we have bases of 5 and 3 on either side of the equation that we definitely cannot create a common base for in order to solve it that way. So what we want to do is we want to take the log base 10, and the reason why we use base 10 is because all of our calculators work in a base 10 base. So we want to take going to take the log base 10 of both sides of the equation. So I'm going to take the log of base 10 of 5 to the power of 3x equals log base 10 of 3 to the 2x minus 1. So now what we're going to do is now we're going to use laws of logarithms and factoring skills and things like that in order to solve for x. So from here, both of these are a power on these values of 5 and 3. So I'm going to use my power rule to rewrite this equation as 3x log 5 equals 2x minus 1. So technically that would be in a set of brackets times log of 3. All right, so the whole idea is, remember, we are trying to solve for x, and so we need to collect our x's on one side. So we want to think of log of 5 and log of 3 as like another variable. So this is like saying a 3x times a, and this is a 2x minus 1 times a b. What we want to do over on this side is we actually want to run this logarithm through my set of brackets. So we have 3x log of 5 equals 2x log 3 minus log 3. Now what I want to do is I want to collect all my x's on one side of the equation. So I'm going to move this 2x log of 3 over here so I can somehow collect it with this expression. So I have 3x log 5 minus 2x log 3 is equal to a negative log of 3. Now my next step is I need to solve for x, and this is like saying a 3xa minus 3xb. The only way I can isolate x is by factoring an x out of these common terms. So I'm going to factor out an x, and I'm left with 3 log 5 minus 2 log 3 equals a negative log 3. My last step is I would now divide both sides by 3 log 5 minus 2 log 3. Now, depending on what type of question it is, at this point, if it was just asked to solve for x to the nearest 10th, then you could just type this value into your calculator. But the question might ask you to leave it in exact values as a simplified as small as possible. So if you want now, at this point, we can now simplify this. Because we have a common base log 10 here, I can rewrite this as log 5 cubed minus log 3 squared and now I can collect these together by using my quotient rule. So technically we have a negative log 3 divided by a log of 125 divided by 9. And so this could be my final answer, or if it was asked to write your answer to the nearest 10th or 100th, on our calculators I would go a negative log of 3 divided by a log of 125 divided by 9. And I get a value of negative 0.42 is my x value. Okay, so depending on the question, it might be, your answer might be shown in terms of a logarithm, or your answer might be asked to the nearest hundredth. So you have to recognize you need to potentially do both. Okay, all right, so moving on to the next question. If we're given 2 times 3 to the power of x minus 2 equals 7 to the power of x. I'm just gonna shorten this up a little bit so we have some room here. All right, so to solve this next question, we're going to do the exact same thing. We can't get a common base in between the 2, the 3, and the 7. So this tells me I'm just going to take the log of both sides of the equation. So log base 10 of 2 times 3 to the x minus 2 equals log of 7 to the power of x. All right, so now in order to isolate x, I want to use my power law here, but I can't use my power law because this exponent is only applied to the 3 value. So I need to separate these values first before I can apply my power law. And so to separate these values, I can use my product law, because it says that if we multiply 2 values, I can separate these with a plus sign. So this would become log 2 plus log 3 to the x minus 2 equals, and then here I can use my power law on the right side, would be x log of 7. Now I'm going to use my power law again, so next step would be log 2 plus, in brackets, an x minus 2 log of 3 equals x log 7. Now again, I want to run this log of 3 through my set of brackets. Now I want to collect my x's on one side of the equation. So I have log 2 minus 2 log of 3 equals x log 7 minus x log 3. So again, my next step is to isolate x, so I'm going to factor out an x. At the same time, if you wanted, you could collect these values together. So I could write this as a log 2 minus log 3 squared, factor out an x, and then technically I'm going to divide by both sides. At the same time, I can collect these as a single log using my quotient rule. So this would be a log 2 over 9 divided by, over here would be log of 7 divided by 3. Would be my x value. Okay, so on your calculator, log 2 over 9 divided by log 7 over 3. As a rounded decimal would be negative 1.78. Okay, so a simplified logarithm or a rounded answer. Okay, so that is solving exponential equations using logarithms. The other type of equation you might get is an actual logarithmic equation. So steps to solving logarithmic equation using laws of logs. So first thing is, with logarithmic equations, you're going to have restrictions on your variable. So you want to identify restrictions on your variable. You need to, in order to solve a logarithmic equation, you have to write each side of the equation as a single logarithm in the same base before you can do anything else. If both sides of the equation are written in the same base logarithm, you can, similar to exponential equations, we can then ignore the log base c and solve the linear or quadratic equation. And then you have to verify your solution. So you have to actually check your solutions for logarithms for any extraneous roots with your restrictions. So you don't actually have to substitute the number in, but you have to compare them with your restrictions, and if they're outside your restriction zone, then it would become an extraneous root. Okay, so we're going to start off fairly easy and then get a little bit complex as we go on. So the first question we're given is log base 10 of x minus log of 15 equals log of 0.2. First thing I'm going to talk about is my restrictions on x. And our restrictions for x, this value here always has to be a positive number. So our restrictions would just be x has to be greater than 0. So now what I want to do is I need to write both sides as a single logarithm. Well, the right side's already written that way. On the left side, we're going to use our quotient rule to combine these as a single log. Okay, so now that these both are written in a log base 10, I can completely ignore my logarithms just like we did with exponential equations and just solve the equation. So x over 15 equals 0.2, cross multiply, x equals 3. I'm going to compare my solution with my restriction. Is 3 greater than 0? Yes, it is. So this would be my solution. If you wanted to check your solution, you could do this graphically on your calculator. So on the left side, I could type in a log of x minus log of 15. And in y2, I could type in log of 0.2. This actually looks okay. Oops. Okay, so I'm looking for this point of intersection. So I'm just going to change my windows. So it looks a little bit better. So I'm finding that point of intersection. And we get an answer of 3. So that's a way to check your answer if you wanted to check it. Okay. All right, next question. So I'm given a log base 5 of x plus 1 plus log base 5 of x minus 3 equals 1. So what I need to do is I need to write the left side as a single logarithm. So I have to combine these together. Well, if I see a plus, then this would be our product law. So I'm going to multiply my two binomials. On the right side, this equates to 1, but in order to ignore my logarithms, I have to write this as a single logarithm, but I want to write it in a base of 5. So if I wrote this as a log base 5, recognize that whatever something evaluates to in terms of a logarithm, the value that it evaluates to represents your exponent on your base. So 5 to the power of 1 would be 5. So log 5 of 5 equates to 1. So now I've written this as a single logarithm. Oh, before we do that, let's just talk about our restrictions before we go any further. Our restrictions on x, this logarithm tells me that x plus 1 has to be greater than 0, so x would have to be greater than a negative 1. This tells me that an x minus 3 has to be greater than 0, so x has to be greater than 3. So the restriction that is going to satisfy the entire equation will always be your larger restriction. So technically all of my x values, my solutions, would have to be a value greater than 0, or sorry, greater than 3. All right, so now that we've written this as a single logarithm on both sides, both base 5, we can now ignore my log base 5s. I'm going to multiply or expand this binomial product to be x squared minus 3x plus x minus 3 equals, and then on the right side we're just given equals 5. So now what we're left with is a quadratic equation. And how do you solve a quadratic equation? We're going to make our equation equal to 0 by moving 5 to this side. And then we're going to factor this. And our solutions for x should be a positive 4 and a negative 2. So now that we have our solutions, now we want to compare these solutions with my restrictions. And my restrictions say that x has to be a value greater than 3. So negative 2 actually ends up to be an extraneous root. So my only solution would be an x equals 4. Okay. All right, so moving on. Given the following, log 4 of an x plus 1 minus log 4 of a 2x minus 3 is equal to a log 4 of 8. So restrictions, let's start with that. X plus 1 has to be greater than 0. So x has to be greater than a negative 1. And a 2x minus 3 also has to be greater than 0. So x has to be greater than a 3 halves. So which restriction is going to satisfy the entire equation? Is going to be this guy. Okay. All right, so on both sides of the equation, we have to write this as a single logarithm of base 4. So we have a log 4 of x plus 1 over an x minus 3 equals log 4 of 8. Now that these are both written as a single logarithm of common base 4, we can ignore these logs and our equation becomes x plus 1 over 2x minus 3 is equal to 8. So then I would cross multiply here. Recognize we got to multiply the 8 through both this entire binomial. So I have an x plus 1 equals a 16x minus 24. I am now going to solve for x. It's a linear equation, so I'm going to bring my x's to one side, my numbers to the other. So this would be 25 equals 15x. Divide by 15, and x works out to a simplified expression or fraction of 5/3. So then I'm going to check with my restriction, is 5/3 bigger than 3 halves? And yes, it is. So then we can circle that solution. Okay. All right. Question D. Again, a little bit trickier. So given the following, 2 log 3 of x minus log 3 of an x plus 3 minus 3 is equal to 0. So, and we are solving this to the nearest hundredth. Okay, so this kind of tells me that it doesn't necessarily work out to be as an exact value. Okay, so first thing I'm going to do is I need to move this coefficient of 2, so I'm going to use my power law. So this becomes a log 3 of x squared minus log 3 of x plus 3. I'm also going to move this 3 to this side of the equation. Would be equal to 3. Now again, I want to write this as a single logarithm. I also need to change this so it's in terms of a logarithm base 3. So what we end up with is a log base 3 of x squared over an x plus 3 equals log base 3 of what value? Right? So remember, whatever this equates to the exponent value on the base of the logarithm. So 3 to the exponent of 3, or to the power of 3, gives me 27. So this would be a log base 3 of 27. Now that we have this written as a common log base 3, we can ignore our logarithms. Equals 27. We can cross multiply. We're going to get us 27x plus 81. So again, we get a quadratic equation here, so I'm going to move everything over to make my equation equal to 0. I'm going to spend 30 seconds trying to factor this, and in fact this cannot factor. So if this cannot factor and you're asked to solve this algebraically, we need to substitute or use the quadratic formula to solve for x. Sorry, before we solve for x, we forgot to talk about our restrictions again. So our restrictions in this case should be x has to be greater than 0, and in this case x would have to be greater than a negative 3. So what is going to satisfy the entire equation would be x has to be greater than 0. Alright, so now we're ready to solve this for x using my quadratic formula. So x equals a negative b, so 27, plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, so this evaluates to 1053. So if you were asked to keep this in exact values and by simplify the radical, so remember how to break down the radical, this works out to a perfect square of 81 times 13. So I have 27 plus or minus 9 root 13, all divided by 2. On my calculator, so to the nearest hundredth, right, substitute into our calculator, 27 plus 9 root 3 divided by 2, we get 21 decimal, oh sorry, 9 root 13, it should be 27 plus 9 root 13 divided by 2, we get 29.72, and our other solution is 27 minus 9 root 13 divided by 2, negative 2.72. So once again, I'm going to compare both my answers with my restrictions. X has to be greater than 0, so this ends up to be extraneous. And my solution would be this. Okay, so just recognize if you were asked to leave this in exact values, then my only solution as an exact value would be 27 plus the 9 root 13 over 2. So this would be my exact answer. This is my answer rounded to the nearest hundredth. All right, moving on to example number 3. It says if log 4 of 1024 is equal to a plus b, and log 8 of 64 is equal to an a minus b, then what is the value of a and b? So when I look at this, I have two pieces of information, this and this. I have two unknowns, so this should be a trigger or a reminder in your head that we need to set up a system of equations. So before I start, I can actually evaluate this logarithm. Log 4 of 1024, so 4 to what power equates to 1024? That should equate to 5. So 5 equals an a plus b. I'm going to evaluate this logarithm as well. Log 8 of 64, that would equate to 2. So I'm going to write this underneath as a system. So 2 equals an a minus b. And now to solve for a and b, I'm going to add these systems together. So my b's cancel. 5 plus 2 is 7. So my a value is, 2a. Divide by 2. My a value works out to 3.5. And now to find my b value, substitute into one of the equations, doesn't matter which one. 5 equals 3.5 plus b. My b value would be 1.5. Okay. All right, and then lastly, example number 4. The number of fish in a lake is decreasing by 5% each year. Okay. As a result of overfishing, write an equation to represent the number of fish present after t years. Use n subscript 0 to represent the initial population and n of t to represent the final population. So when we think of this, a word problem talking about increasing and decreasing, we want to think of this formula, a times b to the t over p, our exponential growth and decay expression,